My name is Elena, and in this AI Lexicon video we'll discuss terms quantized models and full precision models. And it's all about performance. Making AI work faster and use less power is a big deal these days. There are two sides to it. On one side, training the models, and on the other side, later using those models to get predictions or any other results. The latter is actually called inference, and in this video we'll talk how to make inference faster through a technique which is called quantization, so that you can use those AI models on less powerful devices like your phone or your tablet or some embedded stuff. In short, quantization makes computers' job easier by shrinking the numbers AI has to work with. A simple demo of quantization would be if you ask me what is the time, and I could tell you on one side it is 14 hours, 27 minutes, 35 seconds. Or I could just tell you it's 2:30, which is significantly shorter. For the AI model, different variations are possible, but most common is that in quantized models will use integers instead of floats. And by integers I mean 8-bit integer, and by float I mean a regular 32-bit floating point. So how does it work? And you probably already know that artificial neural networks are made of nodes, connections between these nodes, and weight parameters associated with each connection. And these weight parameters are kind of the brain power of the artificial network converted into numbers. And when the information goes through artificial network on hardware, when we do activation node computations, numerous mathematical operations are applied to those numbers, and we need to do all those multiplications and additions millions and millions of times. And we want to make it easier. And to use a strategy of a student who is a bit short on time, we can, for example, instead of doing math with float numbers, use integers. We can say that there are two fundamental representations of numbers in computer memory: integers and floating point numbers. They are stored differently and the operations on them are performed differently. Amount of storage that is needed for integers is smaller, and performing computational operations is also potentially faster. Not to mention that there are some embedded devices which can only support integer data types. So if you were a student, you can easily relate to computers that multiplying float numbers is more difficult than doing the same for integers. Or, to be honest, it's not always the case. As a matter of fact, it's more confusing with computers because it heavily depends on hardware. Obviously, a model quantized to integers will perform much better on a processor that is specialized for integer calculations. However, a modern CPU in a desktop machine does float arithmetic operations as fast as integer arithmetic. However, GPUs, which were initially designed for computer graphics, are more optimized towards single precision float calculations. That's why it's a bit tricky to generalize how much faster quantized models are. Quantization is a way of approximating the parameters by sacrificing precision of the numbers. The more we can approximate, the faster, theoretically, will be the inference. However, this speed gain is not exactly proportional. if we move from regular 32-bit floating point to 8-bit integer, usually the performance jump is not 4 times, but it's actually just 2. And you can also guess that by approximating the data within the model, we probably are making the predictions done by the model less accurate. And in extreme scenarios, the model might not even work or will produce incorrect results. So maintaining accuracy is really critical. And there are metrics to evaluate the effect of quantization on the results of the model, and also a couple of techniques that can help those models which get significant loss in accuracy when quantization is applied to them. So what can you do? First one is a partial quantization, where we apply quantization only for a few layers in the model and leave out the rest of the layers. And this is, for example, done in BERT. Second option is to think about quantization already during the training and to do so-called quantization-aware training and quantize the weights during the training of the model. So all in all, quantization is widely used as a tool to minimize the space needed for the model and also improve the performance of inference. However, for the models that deal with tasks where safety is critical and where the loss of precision is dangerous, this technique should be used very carefully. So this is what quantized models are and how they are different from full precision models.